It's my pleasure to introduce Madhu Athreya. He's the Director of Multimedia Algorithms and Systems at Google. Madhu Athreya is an engineer at Google, leading the development of ISPs for pixel cameras, TPU architectures for on-device Gemini, silicon, and tensor security. He also heads the advanced R&D in video machine learning and generative AI at the Google section. And he's a VirginiaTech alumnus, and his career includes roles at Intel, HP Labs, and Samsung Research. He has a background spanning machine learning, computer architecture, and signal processing. He has navigated the industry's evolution from the AI winter to the current generative AI explosion. So without further ado, it's my pleasure to introduce Mr. Athreya. So please join me in welcoming him.
Thank you. Thank you, folks. Okay, so today's talk is about AI. Isn't every talk about AI these days or the past decade? So anyway, so this talk is about focusing on fundamentals in an uncertain era of AI. So future, how do you sort of position yourself? And this is a conversation I've normally had with my children and who are college going as well, and their friends. It's as to what the future holds and how they should position. So I'm hoping my perspectives and my experience will be of use to you folks as well. Yeah, so my background, VirginiaTech, 1995 graduate, and I went on to Cornell for an MBA, worked at Intel, HP Labs, Samsung Research. Brief stint consulting myself, I did Cruise was one of my clients there, and now I'm at Google. I'll talk about some of the things that I do along during the course of the presentation, but in summary, it's like we make the tensor chips with my phone. So this is the Pixel phone. So we make the tensor silicon that goes into it. So a lot of the cool IPs and enabling cool experiences come from my teams. This is a glimpse into what we do at Google with tensor processor. This is really the TPU architecture that we have developed that is enabling a Pixel 10 phone. It's a feature called as Pro Zoom. It's a very complex diffusion model that runs entirely on device. And we have to develop architectures that can actually capable of running these complex models, either diffusion models or Gemini or other classes of machine learning models. Yeah, so today my talk is a tiny glimpse into the vast space of AI and the AI opportunities. So it's really based on some of the areas that I'm experienced in, and I'm going to talk about those. And secondly, bit of a disclaimer, I've used Gemini to create these beautiful illustrations. You'll see a lot of cool illustrations, right? And as with anything Gemini or LLM these days, you have to be wary a little bit of hallucinations. I've tried to weed out those, but there may be a few. See how elegant these illustrations are, right? It's pretty cool. So AI is transformative. I mean, it's a huge transformative impact, and I think everyone knows that. It's impacting every industry. In fact, the easier list to put on this slide is to say which industry is not getting impacted by AI, and it would be a very short list. I mean, it's going from enterprise software to financial, legal services, robotics. Robotics TAM, Morgan Stanley says, is 5 trillion plus by 2050. And there are two pieces of good news for you guys. It's 5 trillion plus is a huge opportunity. And it's an opportunity that will sort of roll out for the next 25 years. So it's like a major career building pathway. And today, just this year alone, the CapEx spending of hyperscalers is north of $800 billion. So it's again, the insight here is not just about the spending, but the confidence with which these hyperscalers are spending, which kind of shows what sort of promise AI holds for many of these industries. Once again, that should be music to all our ears. Beyond like these sort of commercial applications, there is also this aspect of societal impact, which is quite exciting. This is not an LLM, but it's still in the generative AI space. AlphaFold, for instance, is like broken through and is like able to predict protein structures way faster than humans can. Human crystallography takes about a year. This takes like 10,000x faster. So this year accelerates drug discovery and development and novel protein synthesis. It's like the environmental, like, I mean, these are some cool things I found. They're kind of finding proteins to sort of like degrade even plastics. How do you sort of like have enzymes and proteins do that? Or like create like some more biodegradable proteins. So some really good impact. And some fun with numbers like GPU infra has like grown from NVIDIA's system like it's like 4x, right? I mean, the last 2 years alone, like it's this sort of CAGR you've never seen, and few industries have had this sort of CAGR, especially starting from a very, very high baseline and going north of that. LLM parameters are regularly 3 trillion plus these days. And here's another cool fact. Agentic era is upon us, has been upon us for a few months now. But this was like exemplified by this whole open claw that became viral for these past few months. I mean, the GitHub stars is one metric. It shows 300,000 is like shattered all previous records in less than 100 days. And smartphone transistors these days are like over 20 billion. Like, I mean, this is like the first ever silicon to cross the billion mark was what I worked on like 25 years ago. There was Itanium. So that crossed the billion mark. Now, Itanium was like the size with the packaging was the size of a smartphone. Here, like all these 20 billion transistors is on just a tiny piece of silicon. And this is what is enabling all these new compute and everything that we can put back into these smartphones. So you can actually have like edge inferencing. With all this like great opportunity, also there is this sort of a cloud here. Like this is about the job displacement concerns that are sort of like looming large. And it raises questions about whether AI is really augmenting us or displacing us. Is it sort of taking away entry-level jobs, something that you folks are probably more sort of like tuned to? Or because like AI is like really cannot displace experienced people, more entry level, or is it also sort of compressing wages? I mean, there's also if an agent is competing with me, like do I need to get paid as much? So there are all these questions. So with all this, like I mean, the stock market, like I mean, the software stocks tanked this year, like over 25%. So there are concerns. These are legitimate concerns. So with now, like we have like AI is transformative and major opportunities are being created. Yet there is this job disruption concern. So how does one position oneself for such a sort of like uncertain future? So this is like I said, like, I mean, I've had this discussion with a number of students and who sort of like had at least shared my sort of my experience. So I sort of want to turn back the clock, go back to my own experience. This uncertainty was there even when I was at VirginiaTech. I mean, albeit at a very, very tiny scale. I mean, it's not quite as profound as it is today, but there was uncertainty. As in, the country was really in a recession. 93 country was still in recession, and like over 93, 95 time frame, like it came out of recession. So that obviously creates a whole lot of stress in the system. There are like people who are not graduating because they were not getting jobs and so on. Besides this, my own particular interest was AI. I came to VirginiaTech. I joined Professor Cyrus's team on this project of this sort of like being able to take a natural language and synthesize a netlist or at least an RTL, the whole spectrum. Like I mean, sort of like have what we are trying to dream of today was sort of like was also a promise back then, right? And I was tasked to work on conceptual graphs and very quickly found out like the funding had dried up. And it was not just at VirginiaTech. I mean, this whole space was sort of like coming to a grinding halt. And as we know it, this is the AI winter, okay? So the thing is like my primary interest was gone. And what actually helped me at that time was like I had some other areas that I was also equally interested in. Computer architecture, networks, Besides like the machine learning and neural networks, these were some areas. Image processing and computer vision. We had a fantastic program. Dr. Armstrong had the Spark program, and Dr. Abbott those days, like a computer vision. We had this gigantic the hardware FPGAs and other things to kind of like emulate a whole vision pipeline. So that sort of like gave a fair amount of foundation. And I was also interested. I was interested in cryptography and math, largely because I had tried my hand at implementing crypto software before I joined VirginiaTech. There was like a bit of a stopgap at a research lab, and I found I didn't understand the math at all. I had no clue. I just implemented it, and so I had sort of a yearning to actually go and find out more about the math. So coming into VirginiaTech, I had all these interests, and VirginiaTech gave me these foundations, sort of like had some rigorous fundamentals that helped shape my career. And this today, for instance, it's been very enduring, right, for like 30 years. And I still use exactly the same rigor, that the fundamentals that I learned back then, even today. For instance, like at Google, like we designed the TPU architectures. I mean, they teach you these are ML accelerators, and we have to kind of like get back. Like, I mean, I was interested in vector processors and systolic arrays back then, but that's what we're sort of like looking at: vector processors, systolic arrays, SIMD. How do we sort of like have data parallelism? How do we manage all this data, right? So, and that same architecture sort of like principle applies to whether we're designing the ISP or whatever. So it's like fundamental. And image processing and computer vision is also something that I invested in. It's also very relevant. This is what we are sort of like developing at Google within my team. And that's how we make these cameras happen. Security architecture is also sort of a comeback, a full circle, even though I didn't actually do anything about security of these number of years, but sort of ironically, it's come back, and I'm sort of like working in this space as well. And also, what's interesting is during the course of my career, although I spent my time only in like 3-4 companies, it's not like too many companies, but there have been many different business functions that I've sort of like gone over. Like, I mean, starting from high performance computing to RAS, and then going into mobility and going into robotics and virtual reality and all of this. So each of these are different business areas. And I was able to still traverse through those with the same engineering fundamentals. So it's really relying on what I learned and what I sort of like built on over time. And I also like sort of like my career like progressed through business and technical several times. I'm kind of like, even when I used to lead like M&A technical due diligence, I had to sort of rely on the same fundamentals. Or whether I was like leading research at HP Labs, I kind of relied on these same. So the point I'm trying to make is, for me, it worked for the last 30 years. Like, I mean, investing deep down. And I'm sort of like bringing that as an advice to you folks, that like this is how you can kind of like invest and shape your careers as well. Because what is for sure is you don't know what's going to happen with the generative AI is moving way too rapidly. But what you can do is at least what you're in control of. Like, I mean, so don't sort of like, there are all these other, like for vibe coding and other things are sort of like, that might be of interest initially, but over time, they are not the ones that will sort of like stand the test of time. But anyway, let's take a closer examination of these fundamentals as this AI is evolving and how they apply in the context of the future AI. And so here I kind of like see this whole AI space in 2 broad categories: the AI builders and the AI application developers. AI builders are the ones who are creating LLMs, who are building data centers, who are creating chips, who are sort of like all the infra that goes and the software stack that goes into this whole AI space. And it can also be on the edge too. It's not just at the data center. Then there are application developers. I mean, this is like really adapting an LLM for a certain class of application, be it healthcare or life sciences or whatever, right? And so that's a developer. And in the context of the AI builders, I mean, it's like steeped in foundations. If you kind of like look at silicon design, for instance, it's like really all physics. If you want to invent the next process node, it's all solid state physics. If you want to make a chip, like you have to think about thermals and heat dissipation and everything else. So you really need to kind of like go back to those sort of like brass tacks of the physics and fundamentals. So these really offer a strategic mode. These cannot be sort of like you cannot sort of like wipe code it away over a weekend. These takes many years of really hard work. So sort of like investing in such an area, such deep like sort of technologies can give you that moat. Even on the consumer side, like if the category 2, these application spaces, like you can still sort of like have a specialization, right? I mean, you kind of like do not just become an application developer, but instead you are the application domain specialist. For instance, like the security, for instance, right? I mean, you can kind of like become like a vertical security expert and kind of like build solutions, take LLMs, adapt them, or like build security for LLMs. This is a fantastic example where you kind of like take that specialization and build it. And once again, like these are steeped in the same math and the fundamentals. But something in between is not likely to be very ephemeral. So you need to be careful that you really sort of like have that domain depth expertise. I mean, you can even kind of like think of something like robotics as one such domain. Like, I mean, you can go down all the way and build it really on the application side, but then it has all these technology elements. So let's look at these two in a little more detail. Like, let's say two examples from each categories, like computing and silicon engineering from category 1, robotics and edge AI in category 2. So compute. I mean, this is like, I mean, I've been in this space for like 30 years, and definitely I can agree with this, right? This is the golden era of silicon. It's never been more exciting than now. It's just phenomenal. I mean, if you really think about Moore's law, Kager, it doubles doubled actually. It's not quite growing at that rate, but it doubled every 18 months, the transistor count. But now this compute capacity is growing every 7 months. It's a very, very steep curve. I don't know how long it'll go on, but it's still really going on. Like, I mean, with all the CapEx spending, it seems to be going very fast. So this is, and let's look at how like this computing space has evolved. Like when it started off in a decade ago with AlexNet, that really sort of like stimulated this whole deep learning space and created this opportunity, GPUs, like with, back then it was Pascal, I think. And the whole, it was all image classification, recognition, all imaging related. So even the precisions were all FPs. FP16 wasn't even there. I think just FP32. That was a start, right? I mean, so, but it kind of like caught fire. And then came this whole transformer era. Like, I mean, it's really a seminal paper. Attention is all you need from Google. So this really kind of like started this whole sort of like transformer revolution. And the BERT models were sort of like the thing at that point. Like there were like very different variants of BERT model, mostly for speech and language processing. On the architecture, the GPU architecture side, there was evolution of HBM, and NVIDIA like built this NVLink with, now instead of like one GPU, they had like 8 GPUs, and the whole VRAM like went from 16 gigabytes to 128 gigabytes. So this sort of like really stepped up the game. And now we are in the next era, right? This is the ChatGPT moment. When OpenAI came out with ChatGPT, that kind of like turned the world upside down, right? And so that had massive ramifications to everything, and will continue to have ramifications for the decades to come. And on the hardware side, like for instance, like there were like specific dynamic precisions, and like now it went into rack scale. Instead of like 8 GPUs, has 72 GPUs, and 72 GPUs, a multiple of those into a big pod. So it's like much a higher level of compute performance and scalability. So this is the generative AI era. And it's also during this time, there's this advent of domain-specific accelerators. You've seen like Hennessy and Patterson coined this phrase, domain-specific accelerators, and moving away from really fixed function GPUs to domain-specific accelerators that are more customized hardware that can be purpose-built. But primary drivers are latency, power, cost, and there are like several who sort of like are participating in this. In fact, like Grok just got bought by NVIDIA, and NVIDIA now in the last GTC talked about how it's part of their whole offering. So it's even part of their GPU portfolio is this domain-specific accelerator. The edge as well has seen similar evolution. There is started off with NPU foundations, once again driven by CNNs. Once again, during the time of AlexNet, this MobileNet and some of these mobile class ML models were developed. And these came into smartphones, went into other robots and IoT devices and everything else. And now, like, it's sort of like phase two is sort of beginning and continuing on. It's like trying to bring LLMs to the edge. And this is like really quantizing the models. The thing is, like, here, like, you can trade off some accuracy and perform for performance and size of the model. You can actually get down to even ternary weights on the edge. So that's sort of like, I mean, the architectures are being built to satisfy these models, and so we build these architectures to the TPUs we build. And it's also all heading towards like a much more of a multimodal future. And this is really for the vision language action models. And of course, the vision language action models is a hybrid thing, probably run on the cloud, but there's a whole lot of ML acceleration that happens on the edge for the edge fusion and sensor fusion. There's emerging computing technologies. I mean, some of this you guys are working on. We talked about neuromorphic in your lab earlier. There's photonics and there's analog. Again, you guys have analog CIM and neuromorphic. I mean, so the thing is, like, some of these things are so demanding. Some of these applications are so power sensitive that is really necessary to get into these really complex technologies. And earlier we were talking about like where there is an application, indeed, like robots, right? I mean, robots like usually have this whole issue of like humanoid robots. Like, I mean, this whole vicious cycle of power, batteries getting too big to sort of like handle the power needs, and the batteries themselves causing motors to become bigger, and that kind of like requires more energy. And so it's like a vicious cycle. So these things have to be solved for every part of it, including compute. And memory, a lot of this is like gated by memory. So memory is really important. Like, I don't know if you guys have seen Micron stock shoot up this year, right? It's all about my memories and the crisis in memory. And but the thing is, like, at a compute standpoint, like, there's a huge amount of like compute that is really memory bound. And to solve this, of course, like, I mean, there's a huge progression from HBM4 to 5 and LPDDR from going to 6, 5 to 6 and to 7 someday. But it's also, again, like, there are disruptive technologies here. Process, once again, like, this is something that you guys are seem to be working on, near memory compute and process in memory compute. These are really needed for the future. Like, we're sort of like really driving those efficiencies to bring that $5 trillion robotics TAM to sort of like reality. You need to have such fundamental innovation. So anyway, so this is sort of like a general overview, but let's look at under the hood for what we do specifically. So let's say in our architecture development phase, we start with an ML model. It could be an LLM, it could be Gemini, or sometimes like we develop our own ML models within our team. Like, I mean, it really depends. Like, I mean, it could be a diffusion model, but it goes through a full loop. Like, I mean, you characterize a model, look for hotspots, and come up with some architecture proposals and update the compilers, try to sort of like validate the architecture proposals, and then see if we have reached the target. And it's a very iterative loop until we sort of like optimize. But the thing is, here we might be optimizing the LLM, or we might be changing the architecture of the ML model, or we could be changing the architecture. It's like, that's why it's a very close hardware software co-design. So this is normal process. Like, every generation we go through, every model that comes to, we sort of like go through this same iterative process. And in all this, like, we kind of like go look deeper to like look at this model to say, like, what is a memory bound, what is compute bound. For instance, an LLM, like, for instance, like a prefill stage is compute bound, whereas decode stage is autoregressive. So it sort of like is memory bound, because for each word it has to predict, it has to look for the previous one. So there's various techniques that we come up with. For this memory bound, for instance, we have to have KV cache. So we don't recompute the KV cache every time. So we sort of like make some appropriate choices. We make some appropriate sort of like model systems level choices, as well as architecture level choices. And then, of course, we kind of like go and have a whole Pareto of architecture, so that we kind of like look at like whether we should build a CNN accelerator, or should we have like a matrix multiplication that will serve as a CNN accelerator? Should we have a systolic array, or should we have SIMD vector processors? And so a lot of these things, like, I mean, as part of this loop, we go through all these considerations. Anyway, this is sort of like how a modern SoC, smartphone SoC looks like. We have like various compute entities, CPU, GPU, NPU, DSP, and so on. And then a bunch of fixed function accelerators, codecs, and image processing, ISPs, and so on. Right? And these sort of like serve different market segments, camera, AR, VR, robotics, depending on the size of each of these compute elements. But the point is not to sort of like give a survey of all these. So like you are probably more familiar with many of these things than I am, but just to kind of like bring back my point. But in each of these things, it sort of like requires competencies like with architecture expertise, algorithms, design and verification, ML model developers, modeling. So like a ton of opportunities in these. And none of these opportunities can easily be displaced by AI, right? We embrace AI, we sort of like use AI to sort of like help with these things, but they don't necessarily sort of like eliminate the need for such experts. It's really needed. And let's look at this robotics, which is in the category 2, the consumption side, right? So robotics, as we said, like it's a big market, and there are going to be like 1 billion robots. So it's a lot of work ahead. And now the big change, robotics is an old field, right? Like for 50 years, 60 years, the robots have been around, industrial robots, very precise, very rigid. They were sort of like in a very structured environment in a factory doing XYZ tasks, well programmed. But now LLMs are sort of like ushering in a new era of robotics. This is about like really a general purpose robot that can navigate in a fully unstructured environment like a cluttered home or office or a factory floor and be able to do different tasks. The same robot like is not like task specific. They can kind of like go and pick up different tasks. And these are like robots that are controlled by sort of like a task given by an LLM or a VLA, and they have world modeling, so they have an understanding of how the world, the physics of the world, they understand that through world modeling, and they have this real-time sensing to be able to make effective decision making. So this is sort of like how this human robots and the entire robotic space is evolving because of this new LLMs. And LLMs are being used for training and all kinds of deployments. But at the same time, while it seems like humanoid robots have already arrived, the reality is it's far from the truth. There are just so many problems yet to be solved. So it's not like, I mean, this is like, all I'm saying is like, this is like a fertile ground for innovation for the decades to come. There are so many areas. Like, I mean, let's just look at one aspect of this, self-awareness or proprioception. So because again, I'm trying to sort of like bring back my personal experience. So I used to run this HP Labs robotics team, and we sort of like had to solve a problem for our 3D printers. So 3D printing, like I mean, HP, like so it's sort of like the way it's done is like it sprays a powder bed, then it so like the regular inkjet, so like sort of fuses, senses bonding agent, and next layer is of powder is sort of like laid on top of it, and then the ink is sprayed. So as a consequence, after the entire print job is done, you get this big cake bed, powder cake bed, and all these objects that are printed are sort of like suspended inside it. Now, the robot that we had to build was to sort of like pick those objects, and with an air jet, we had to clean the robot. And this is not a very trivial task because these 3D printed objects usually are like have a lot of lattice structures and so on, because of you need to sort of like meet some cost targets and weight targets and so on. There are other considerations. But the thing is, the powder is all clinging to all these little nooks and cracks, and these need to be cleaned. Now, it was all fine until we sort of like polymer, we kind of like managed to sort of build something that made sense. But then metal parts, like something that's a little more fragile, we had this issue, like with the robot handling could damage the part. And we just didn't have haptic feedback. We didn't have any issue. And at that point, I didn't know it was called a proprioception gap, but evidently it is a proprioception gap. And so we just had some kludgy solutions that didn't quite work well, okay? But today, those problems are being tackled, and still, I don't think it is a solved problem. It's still being solved. But once again, the way it works today is like a humanoid robot or any robot is filled with a bunch of sensors, vision, even like foot sensors, and like there is acoustic sensors in the foot. footpad microphones and so on, right? And so there's a whole amount of signal processing that's done to clean the signals. And then there is machine learning and reinforcement learning that kind of like is able to aid the robot. But what happens is like the LLM and VLA kind of like provides a task saying like, hey, walk across this one to do XYZ things. And the world model says it will analyzes that space and says, okay, it's all hard turf, no problem, just walk there. And then somehow like it's missed this patch of mud and the robot goes there and steps in it and suddenly it's losing its balance. That's when this reinforcement loop kicks in. It needs to kind of like go and take the sensory input, make some quick adjustment. Like, I mean, it's a really fast closed loop that has to happen. And then of course, these are updated back into the world model LLMs and VLAs. Once again, the point is not about a technology survey, right? I mean, the point is, again, competencies that are needed. It's again, the very same competencies, signal processing, computer vision, architecture, audio-visual sensing. You can go, the sensing itself, there's a fair amount of opportunity for innovation. And although also on the machine learning side, like, I mean, there's just all these LLMs and VLAs. Again, it's an unsolved problem. For instance, Fei Li has this whole startup that's doing this whole with a G-Splash. She has this sort of like many G-Splats taking this multiple images and creating a 3D world. So that's all used for robot training and robot, in fact, like even while it's in operations. So it's not just Fei Li, NVIDIA, Google, Genie. There's just so many people working on this simply because it's not a solved problem. There's just a lot of work ahead. Anyway, so compute and robotics. Let's just see the intersection very quickly. So there's a fair amount of compute that goes on the robotics. Once again, the power, cost, latency are all key considerations, DSPs, GPUs, ML accelerators, and neuromorphic processors, right? So these are all sort of necessary. So those of you working in this space can have a direct applicability, even if you're not roboticists, or those of you working in robotics can kind of like embrace this computing and ML acceleration. And this is, of course, not just on device because of this world models and LLMs and VLA, they're all running in the cloud. So having an efficient architecture that kind of like spans between the edge and the cloud is very important. And again, it's a very hard problem because you want the edge to have the context of the cloud. At the same time, you cannot go and rely on the cloud at this fast latency, short latency that is needed on the edge. So it's a challenging problem. These are the problems that many are trying to solve. So, and then another area of compute here is data generation. The thing is, unlike like even self-driving cars, I mean, getting data is relatively easier because you had a lot of data available, and cars, you could stick a camera and get a lot of sort of cars egocentric view of the data. But that's not the case with robot data. Getting the robot data is having some very complicated teleoperation and how many, it's a scaling problem. You can't get a whole lot of data that way. And human internet data is not really high quality, although there's a fair amount of work going on in terms of looking at like training a robot, just watching some videos. But that's the reason there's a fair amount of work in the synthetic data space. As I mentioned, Fei Li's work is sort of like targeting this area. I mean, even NVIDIA talks about compute in these three areas that are needed. So for this, like edge compute, cloud compute, and data generation. Okay, so final advice. So these engineering fundamentals have worked for me, and that's the best advice I can give going forward. Like just find the areas that you're working on, whatever you're working on, go deep and have a solid grounding while you're in school. This is the best place to sort of get that sort of education and shape your career. Don't chase some vibe coding hype that comes along. That's not going to sort of like be around for very long because another agent will do the vibe coding and sort of like displace that job, right? So stay the fundamentals. AI builder category, there's a lot of opportunities. It's intrinsically steeped in these fundamentals. But if you want to be on the AI applications category, sort of like pick a domain, so like go deeper on this domain. And finally, embrace AI, right? To just sort of anything that we do, even to sort of gain a deeper understanding of fundamentals, embrace AI. For instance, we use AI quite a bit. We use Gemini quite a bit. Even in our architecture sweeps, we use AI. We will look at what's the best way to sort of for a given precision to work. For a certain model, we use AI. So there are plenty of places we use it, and that we really sort of helps us. And so that's why we should get away from that fear of is AI sort of augmenting us or replacing us, to really make sure that it's augmenting us. Use AI to sort of make sure we do better. Okay, thank you.
Thank you very much. Okay, any question? Maybe I can start. So I'm curious about the edge computing limitation that, not limitation, but what is the state of the art when it comes to edge computing? How small the models are getting to right now, and
you mean the LLMs?
Yes, and what do you see in the future? Are we how does the future look like when it comes to edge computing?
So edge computing will always run a much smaller model than cloud computing, right? So we are talking about anywhere from 1 billion parameter to 2 billion, and maybe someday it'll be like a few more billion. So that's not going to change a whole lot. Okay. It could potentially change if somebody were to build a purpose-built device, not a phone or anything, but kind of like an edge agent that has a lot more capability. But even then, we're talking about maybe 16 billion parameter model, and then some smaller set of tokens. But the thing is, what will certainly happen is that there will be a smart way of partitioning the workload between the cloud and the edge, because you cannot send all the queries to the cloud, and that's sort of really going to increase the cloud costs. It's going to sort of really, all these CapEx numbers, even then they won't be able to satisfy these demands. Now imagine it's humans who are actually sort of sending all those tokens upstream. Imagine if my agents, half a dozen agents, start to harass the system every half an hour, sending requests. So at that point, there is efficiency that comes into question. Can kind of local agents can do most of their work with the smaller models on device, and that's where it is going to go.
I see. So it's very interesting area, and I see
Yeah.
a lot of growth there.
Indeed.
Yeah. Any other question?
So, I mean, with respect to edge computing, right? I think the goal is to probably reduce the compute to a particular small device like a mobile phone. But right now, this is probably a business-related question, but right now all the models are monetized based on tokens or compute power or whatever it is. But when you bring it to a small device like a mobile phone, how does Google view it? Are we going to be charged based on the amount that you spend on your mobile phone, or how is it going to be?
It's
What do
an
you think?
interesting question. I am least qualified to answer that, and even if I could, I wouldn't answer that question, right? But the thing is, let's say, just looking at this, right? So the cloud, it's not entirely monetized that way per token. If you really think about their subscription models, if you kind of say Anthropic $200 a month, and if you go and try to deluge it with a number of tokens, their business, the $200 is not going to be enough to serve all those tokens. So it's for Google or whatever subscription model. So it's assumed about a finite amount of tokens that's going to come from the users, right? So now if you start to sort of exceed that, then those models will change. Now, if you kind of really truly make it per token, then the user's cost will go up. It will really get inflated. On the other hand, users have paid for this device. It's your compute, right? So it really shouldn't be a monetization. But I don't know. I have no idea how this will be monetized.
Okay. Yeah, thanks so much.
Thank you. I have a question from Zoom.
Okay, from Zoom, from Scott Midkiff. Great talk. How does your power consumption play into the design of chips, algorithms, and models in this work? This could be to extend battery life for smartphones or reduce the impacts of data centers.
How will power play? Yeah, it's just profoundly, right? I mean, this is like one of the fundamental barriers, if at all, right? I mean, look at the data centers, like all these hyperscalers are investing in buying up nuclear power plants and having like onboard power, right? I mean, and the same thing is on the edge. Like, I mean, we are really challenged by the battery life. If we really wanted to have like build an agent that could kind of like really understand our needs all day and all through the S1, like, I mean, it's like a battery life is going to be key. I mean, the battery technologies are not improving at the pace at which these use cases are. So it's really going to become even more of a bottleneck as we sort of scale those models, right? So it's one of the most fundamental challenges we're having to. Batteries and thermals on these edge devices, these are the biggest challenges we have to face. I mean, thermals for peak use cases, and battery life for all these long duration use cases, all day use cases.
Yeah, it's interesting. Even for the data centers, it looks like the power supply is not matching the demand as it should be. And I think what I'm hearing from you is that even the battery technology is not also matching the growth in edge computing as it should be.
Yeah.
So it looks like the improvement has to happen on the demand side, not on the supply side, and on the model development, how to make the model as with less number of memory as possible and less power.
Exactly. Or like go into something like the technology improvements, like do in-memory compute so you don't burn as much power going to DRAM, right? So you have to do those. That's the reason why, even though these things have challenges, like everyone's looking in these directions. Having analog multipliers is, yes, there will be sort of like precision challenges and so on, but it still might be acceptable trade-off if you want to do other things.
Any other question? Yes.
Thank you. Thank you for this talk. This was very informative from industry perspective. As you know, I'm from neuromorphic computing domain. So my question is, does the current industry, in your vast experience, see that there could be an end to the energy resources which these current generation AI systems are needing? For example,
I would know. I mean, I read all that you read. I have no idea beyond that. I know there's sort of like a loop. We have an energy crisis in general, but maybe there are alternate sources. Maybe this nuclear sources.
Yeah, for sure. So with all these alternatives to clean energy, at the end of the day, they also end up polluting the environment. And for the same reason, there has been a lot of opposition to like not to set up data centers and whatnot. We frequently read these news articles. So if this goes on and it seems like it's going on anyway. So what would be the next step for the AI industry in the wake of, say, constrained energy resources?
Yeah, again, I would only have to guess, just like you, right?
Okay, thank you.
Thank you for the talk. So my question is, do you have any preference between the AI builder side or the application builder side? I know you mentioned the two different applications of AI.
I don't necessarily say I have a preference. I mean, I have obviously a bit more knowledge on the AI builder side, having been on the silicon development from HPC to S1. Like, so I've kind of like been in that space. So there's, and also robotics. But the AI applications have, once again, my intuition tells me that you need to be strong domain expert, right? You cannot sort of just be a middle person developing some high level applications. It has to be a lot more steeped in fundamentals.
Thank you.
So I'm going to ask a question on behalf of our students. Do you have any tips on how to land a job at Google?
Google, you guys are all doing really amazing work. Like, yeah, you apply. I think you all have a shot.
Any like special tips, like maybe you would advise your son,
Special tips,
son
again,
or
like, I
daughter?
mean, Yeah. Sure. So the thing is, like, I mean, look at the areas that Google is investing. Those are going to be the higher growth areas for Google. I mean, for instance, like, I wouldn't be surprised if Google needs many more or TPU architecture on the data center side and data center rollout. So there's a lot of growth happening, right? I mean, where will all that capex spending happen to happen, right? I mean, that will require sort of new engineers. But that doesn't mean, like, I mean, other areas of Google are not hiring, but I'm just saying position yourselves in this. That's the thing. Again, align yourself on these fundamentals and sort of like these growth opportunities that probably makes you a better candidate for companies like Google.
Right. Any other question? Do we have questions in Zoom? We have a question there. Yeah, 1 second.
Yeah, thank you for the talk. You mentioned on one of your slides that there was, like, in the 90s there was a downturn in AI. Based on, like, given, like, current economic situation and, you know, what's going on, like, for example, I think today, like, Oracle's laying off 5,000 employees or something. Do you think we're about to reach another, like, wave, like another crash in AI soon, or is that?
So first of all, my objective of showing that slide was not to sort of like predict another downturn. Far from it. I was just kind of like talking about the uncertainties that I faced during that time because of the downturn. Okay, and secondly, yeah, there's a lot of very heated debate about whether AI is a bubble or not. And once again, I'll be just one other person guessing here. And I have my stock invested in Google and other hyperscalers, and I'm betting for a more optimistic future, personally.
Hopefully, yeah.
Thank you. Any other question? Do we have question in Zoom? All right. In that case, we have reached to the conclusion of the talk. Thank you very much. Really appreciate it. Thank you.
Thanks.